I'm Sean Rager, and this is my Lab 5 for Georgia Tech Physics 2, Magnetic Braking with Faraday. Looking at our overview, we'll start with an introduction to our experimental statement, and then follow up with some physics concepts, our real-world experiment, and data gathered. Then we'll move on to our glow script code and the models it produced. Finally, we'll finish with results and conclusion questions. For this lab's topic of investigation, we will be using Faraday's law, which shows us that a change in magnetic flux over time within a conductor will induce an electromotive force, referred to as an EMF, and thus a current within the conductor. And we also know that this current will create a magnetic field of its own in the opposite direction to the changing magnetic flux. And we'll take advantage of these two principles in both the real world and glow script to show an interesting phenomenon when a magnet falls through a cylindrical conductor. Our real-world experiment was as simple as dropping the magnet north side down a tube of aluminum foil and recording its entrance and exit times. We repeated this trial 5 times in a row to get an average time of 0.97 seconds. We also took dimensions from the tube's length, width, and inner radius, and we measured the mass of the magnet. For the magnetic dipole of the magnet, we reused the value of 2.1 amperes meter squared from Lab 3. Our physics concepts for this lab were derived from the Biot-Savart law and Faraday's law, for this situation where a bar magnet is falling through a cylindrical conductor. First, our magnetic field equation related the magnetic dipole moment of the bar magnet, as well as the radius from the magnet to a point on the ring of induced current of the cylinder, to get the magnetic field vector at that point of the cylinder. Next, the time derivative of flux equation utilized the magnetic dipole moment, the vertical distance from magnet to the ring of induced current, the velocity of the magnet, and the radius of the cylindrical conductor to give us the EMF that is produced for that ring of induced current. Next, we use that EMF and Ohm's law to derive the current value for that ring of induced current. Next, we used the induced current, the radius of the cylinder, the magnitude of magnetic field at that ring, as well as the angle between the y-axis and the vector for the magnetic field at that ring to find the force on the loop, and then use Newton's third law to find that the force of the magnet would have to be the inverse of the force on the loop, and then finally use Newton's second law to find that the net force on the magnet would be equal to the force of gravity plus the force on the magnet. Next, let's look at our functions and models in glow script. I wanted to highlight the 3 functions which correlated to our 3 main physics principles. The first, finding the magnetic field at the ring of induced current. Next, finding the derivative of flux over time at that ring of induced current in order to find the current. And finally, deriving the force on the magnet from the inverse of the force on the ring. Our models ended up as both this graph and this figure. First, looking at the graph, which relates velocity to time, we can see that it took 1.03 seconds for our magnet to fall through the tube of cylindrical conductor. And next, we can see a freeze frame from a video of our magnet falling through the cylindrical conductor. The red end correlates to the north end of the magnet, and the blue end correlates to the south side. For our results, we can see that our real-world and glow script values were pretty close to each other, with only a 5.8% error, which can be due to factors such as the tube being made of aluminum sheets rather than solid aluminum, the magnet not being dropped perfectly on axis, and the limitations of a phone camera for detailed frame analysis. Now finally, we'll look at some conclusion questions. First, what if the resistivity of the conductor was reduced to as close as possible to 0? How would the dynamics of the falling magnet change? And looking at our Ohm's law equation, if resistivity was close to 0, then we would see that the induced current would be very, very high, and as this current controls the magnetic force from the tube onto the magnet would have a much greater upwards force and would travel much more slowly down to the ground. And if we cut holes or slots in the tube, we could think this would change the situation because our tube would have less continuous circles of conductors, and therefore this would decrease the overall ring currents as the magnet is traveling through and trying to induce currents within the tube. This decrease in induced currents would decrease the magnetic force as it's dependent on these currents for its generation. There would be less upward force on the magnet, and the magnet would fall much more quickly through the tube. This concludes my Lab 5 for Georgia Tech Physics 2. Thank you for watching.